Imagine you are baking, and you accidentally dump a cup of fine beach sand into a bowl of white sugar. You stir it up. You now have a perfectly uniform, completely useless pile of grit and sweetness. Your hands are too clumsy to pick out millions of individual sand grains. If you pour the mix through a kitchen sieve, both the sand and the sugar fall right through the holes. To fix this, we have to rely on a core rule of chemistry. Mixing sand and sugar does not create a new chemical. The grains are just sitting next to each other. We can physically pull them apart. Because they haven't reacted with one another, every single grain of sand and crystal of sugar keeps its original size, weight, and shape. We don't need magic to separate them. We just have to identify the physical properties that make them different and select the right tool to pry them apart. Think of filtration as your net. It traps solid chunks while letting liquids pass right through, sorting materials purely by particle size. Evaporation is your escape hatch. When a solid is completely dissolved in a liquid, heating the mixture turns the liquid into a vapor, leaving the solid safely behind. For dry solids, sieving catches large pieces and lets small ones fall. Winnowing takes advantage of weight, using wind to blow the lighter dust away while the heavy seeds drop straight down. Magnetic separation is highly specialized. Here we see a crane magnet yanking jagged iron and steel waste straight out of a chaotic pile of trutch. People often assume magnets attract all metals. They don't. But a magnet will completely ignore aluminum, copper, and brass, making it perfect for targeting iron-based materials specifically. Sedimentation relies on gravity to slowly drag heavy, insoluble solids to the bottom of a liquid so you can pour the clear water off the top. Churning speeds up separation by spinning a mixture, driving lighter fats away from denser liquids. Every tool in a scientist's kit is built for one specific job. Each one attacks a single physical vulnerability: size, density, magnetism, or state of matter. Let's go back to our bowl of mixed sand and sugar. Since no single tool can separate them, we have to chain a few together. Step 1. Add water. Sugar is soluble, meaning it easily dissolves and hides within a liquid. Sand is insoluble. It ignores the water entirely and stays piled at the bottom. Step 2. Pour the wet mixture through a filter. The barrier easily traps the solid sand, while the dissolved sugar slips right through the tiny pores along with the water. If we had tried pouring the dry mixture through that same filter without adding water first, the small sugar crystals would have fallen right through the pores alongside the sand grains. Sequence is everything. Step 3 is evaporation. We apply heat to the filtered liquid. The water turns into a gas and rises into the air, leaving dry sugar crystals behind in the pan. Some people think the sugar will evaporate too. It won't. Water is a volatile liquid, meaning it readily turns into a vapor. Sugar is a non-volatile solid. It requires massive amounts of heat to melt, let alone vaporize, so it stays put. By lining up simple tools in a logical order, dissolve, filter, evaporate, we easily untangle a physical mixture that seemed permanently ruined. You use this exact sequence in your kitchen every morning. When you make coffee, hot water dissolves the soluble flavor compounds from the beans, and a paper filter traps the insoluble grounds. Inside your body, your kidneys do the exact same thing. They act as a highly advanced filtration plant, pushing your blood against a microscopic barrier to trap essential cells while letting tiny liquid waste particles pass through. Here we see massive, colorful evaporation ponds built directly into the landscape. This is how the salt industry extracts solid salt from seawater on an industrial scale, letting the sun slowly turn the ocean water into vapor. From brewing a cup of coffee, to cleaning your blood, to harvesting miles of ocean salt, the physical rules of separation operate exactly the same way. Let's test this with a final puzzle. Imagine a dry pile containing sand, salt, and jagged iron filings. Before you do anything, how would you isolate all three materials? Step 1. Use a magnet. By pulling the iron out first, you avoid dealing with wet, rusty metal later. Step 2. Flood the remaining sand and salt with water. The salt easily dissolves into the liquid, while the sand sits at the bottom. Steps 3 and 4 are familiar. Pour the mixture through a filter to catch the dry sand, and boil the leftover liquid to evaporate the water and recover your salt. Untangling the physical world isn't about using a single perfect machine. It is about knowing the specific properties of your materials, grabbing the right tools, and planning the perfect sequence.